However, that was inverted, note about that. So then we can ask ourselves, what is the ideal optical imaging system to us? For that, we already said there's an object. If there's a light, scattered light, or if it's fluorescent object, emitted light, from point by point, those light emission will be in fact going outside of the world like this diverging fashion. But if we have a proper optical element or imaging system, we can call it, it will match this one to converge down to each corresponding point and focus so that we can form an image. Then you can ask about, hey, then I can have infinity amount of information of the object space if I have proper optical elements. That's a very good thought. We have to think about what can be a limitation for this type of ideal imaging system. So ideal imaging system means each point in the object should be mapped onto a single point in the image. The question is the fidelity or the size of this infinitesimal point can become again infinitesimal point, which means like infinity of resolution. So currently you can think of, let's say, these are objects are composed of molecules, and molecules composed of atom composed of like nucleus and electron. Yeah, those are objects. If you can map those one by one, you can have almost infinity of resolution. Why that is not possible? This is very important for whoever deals with an imaging system, talk about it. That's about resolution. So in the real world, the imaging system actually does not focus perfectly. That's a problem, and we have to know where comes this limitation. What do we, how we can overcome this limitation? Okay, so first of all, as I said, geometric optics, which we will talk about it, like the one with the interface and lens, that is very ideal. So it doesn't show anything wrong and anything which degrades the resolution of optical system. But remember, the light we are dealing with has a duality. Either it can behave like particle light, it can behave like a wave. Remember, all the waves having a property when it interacts with an object, it should diffract or bending property. So in fact, why we cannot get infinite amount of resolution by this optical element is first, we are using light as a medium, and light is a wave, possess a wave property. And when they deal with optical elements, these optical elements are finite. So it's a finite object. The wave will be diffracted as somehow. And that is a fundamental issue of optical imaging system. By using light, which has a wave-like phenomenon, because of that, there's a fundamental limitation of resolution. So the resolution really depends on the wave property of light, which is wavelength lambda. So remember, that's the key issue, that why we cannot focus perfectly. And of course, when you generate this optical imaging system, what happens is you cannot align it totally perfect. And also the lens over there, we manufacture the lens, and the lens is not usually perfect lens. The easy way to manufacture a lens is making the surface as a spherical way. So spherical lens we call, or convex lens. And that lens, if you use geometric optics, you realize the rays will not be perfectly focused down, because the surface of the lens, what we make a spherical shape, is not in fact ideal. So those imperfections in image formation we call aberration. In Korean, it's called sucha. So aberration can contain many aspects, but these two are the major cause of why we cannot have, let's say, 1 nanometer resolution 1 angstrom resolution with an optical microscope. So this is something you want to have a fundamental, here a fundamental limit is of course diffraction limit. Because aberration, somehow if you are using poor optics, you can use more expensive or optics. If it's a spherical aberration, you can buy aspheric lens, which is much more expensive. So you can actually reduce this aberration. But somehow diffraction limit means the light is bending when it interacts with an optical element. And that is a fundamental wave nature of light. So it's kind of hard to overcome.